Hello dear students, hope you are all doing well. I'm Mr. Idris, your physics teacher. I'm back again with another video lesson. In a previous lesson, if you remember, we stopped it here in eddy current, and today we are continuing to explain the eddy current, and we are going to solve all questions of the section review in section 1 in chapter 6. Eddy currents. What is eddy current? The last topic in this section. Eddy currents, a circular induced currents within a conducting material. What is eddy current? A circular induced current. This circular induced current induced by changing magnetic flux of the external magnetic field when acting on a conducting copper object or copper material. So in this case, by changing the magnetic flux over the conducting copper material, this circular induced current produces. This circular induced current is called eddy current. The applications of eddy current is very important, and this question has been brought in the Wizawi exam many times. Be careful. And the question says, what are the applications of eddy current? Eddy current has advantage and disadvantage. So the advantage of the eddy currents and the applications of eddy currents in furnaces. Eddy current can be used in the furnaces like for heating or warming. Because this circular current, this eddy current, will convert into the thermal energy, into the heat, because of this current, because of the resistance changes into the thermal. So that is why it can be used in the furnaces. The second application of the eddy current, car brake systems. In a car brake system, also the eddy current can be used because of the opposing magnetic field or opposing induced magnetic field that opposing the external magnetic fields. That is why it can be used in a car brake systems. And also eddy current can be used to detecting metals in airports or in underground. What are the disadvantages of eddy current? We studied the advantage, the applications of eddy current. Now we are explaining the disadvantage of eddy current, because as I told you, eddy current has advantage and disadvantage. The disadvantage of eddy current is losing energy or power dissipation by eddy current in transformer, in motor, because this eddy current, it goes to dissipate and losing the energy as the power of the generator or electric. The disadvantage of eddy current, the kinetic energy due to the motion of the conducting material. Due to what? Motion of the conducting material inside field is just converted to the heat energy which distributed within a material. So another explain for the disadvantage of eddy current and answer of eddy current. Eddy currents can cause significant energy losses in the form of what? Heat. The energy can be the electrical energy can be converted to the thermal energy by the eddy current, and this losing of energy, it goes to decreasing the amount of the current, and it goes to warm the object when they flow through the conducting material. This particularly problematic in the transformers. This power dissipation will occur in transformers, in motors and generators, where it reduces the efficiency. It goes to reduce the efficiency of the power. Explain how eddy current produces when a conducting bar moves in a magnetic field. In the presence of changing magnetic flux, this eddy current, this circular induced current, produces in the conducting material. When conducting bar moves in a magnetic field, the electromagnetic induction that arises due to the variation of the magnetic flux or fields leads to induced a circular motion. Circular current. This circular current within the material that resists the original variation of the flux, and this phenomenon is called eddy current. What is the electrical guitar pickup operation based on electromagnetic induction? Guys, we finished this section 1 in chapter 6. Now we are going to solve questions of section review, section 1 in chapter 6. Question 1, a circular current loop made of a flexible wire is located in a magnetic field. Describe 3 ways an EMF can be induced in the loop. If you have a flexible wire with a magnetic field, in how many ways we can induce the current in this coil? Moving, the first way, moving the loop into or out of the magnetic field by moving in or out of the magnetic field, we can induce the current in the loop. The second way, make the wire into a coil and rotating the loop with the magnetic field. The third way, changing the strength of magnetic field. Why? Because when the magnetic field strength changes, magnetic flux changes. When magnetic flux changes, it goes to produce induced current in the circuit. By changing the strength of the magnetic field, also we can induce the current in the coil. And changing the shape of the loop or area of the loop. By changing the area, also we can induce the current and EMF in the circular loop. Question 2. A bar magnet is positioned near a coil of wire as shown in this figure. Okay. What is the direction of the current in the resistor? What is unknown? The direction of the induced current in the resistor. We have a bar magnet and we have a coil of wire. We have two situations. When the magnet is moving to the left, this is magnet. Okay, it has north, south, and this is a coil of wire. A coil of wire. This is resistor. What is unknown? Branch A, where when the magnet is moved to the left, magnet moved to the left, magnet moved to the left. It means to the left. It means moves away. When a bar magnet moves away, when the north pole of bar magnet, as the Lenz's law stated, when the north pole of bar magnet moves away from the end of the coil, the end becomes the opposite pole. Okay, this end becomes opposite pole, south, and this end will be north. Okay, if you know the direction of the magnetic field, according right-hand rule, you can determine the direction of the current in the resistor by using right-hand rule. The direction of the magnet, the north pole is located here. Put your thumbs in the direction of the north pole, and the four fingers is downward above the iron rod. Is downward. Where is the direction of the current? The four fingers is downward. Okay. So the direction of the current is downward because you have to close your hands. Okay. Current is downward. Downward here. The direction of the current in the resistor from left to right. From where? Left to right. The direction of the current in the resistor is directed from left to right when the north pole of bar magnet moves away from the coil. In the second case, the same magnetism, north-south, a coil of wire, wrapping wounded with a wire. Okay. In the second case, when the north pole of bar magnet is moved to the right, in figure B, is moved to the right. When the north pole of bar magnet is moved to the right, it means the north pole approaches the coil. According to Lenz's law, when the north pole of a bar magnet approaches the coil, the end of the coil becomes the same pole of the bar magnet. We approaches north, and this end becomes what? Becomes north. It becomes what? North. If this end is north, this end is south. Put your fingers and your right hand rule, the thumb is in the direction of the north, and the forefinger, because this is north and the four fingers above the iron rod, it should be upward. According right hand rule, north, your thumb is north, and the four fingers is upward. Upward. The direction of the current is reversed, and the direction of the current is directed from right to left. In this way, you can find the direction of the induced current in the resistor. One of the very good questions Be careful. Question 3, 25. Question 3, at 256 turns, number of turn. Question 3, number of turn. Number of turn is 256 turn. Coil with a cross-section area 0.0025 meters square. This is area 0.0025 meters square. Okay, is placed in a uniform external magnetic field of strength 0.25 Tesla. B 0.25 Tesla, but we don't know this is B initial or B final. So you have to read all the questions. Okay, so that the plane of the loop, the plane of the coil, perpendicular. If the plane of the coil or plane of the loop is perpendicular to the magnetic field, angle is equal to 0. Because plane of the loop is perpendicular to the area vector. When plane of the loop is perpendicular, area vector is parallel. When area vector is parallel with the magnetic field, angle between A and B becomes 0. So the coil is pulled steadily out. What do you mean by coil pulled steadily out? It means that B to 0. So that is why this one becomes B1. In the case when the coil is pulled steadily out, it means that this coil is not inside the magnetic field anymore. It's pulled steadily out and B final B2 becomes 0 of the field. In 0.75 seconds, delta T, the time that takes to pulling out this coil, 0.75 seconds. Find the average induced EMF during this time interval. Average EMF during this time interval. Guys, look at the question. What is unknown? EMF. So in this question, area or magnetic field changes. The magnetic field changes. Okay, from 0.25 to 0, magnetic field decreases. If magnetic field decreases, becomes negative. When delta B is negative, EMF positive, current is positive. Without solving, you can know that this is positive. The final answer of EMF must be positive because delta B decreased. So you have to use this relation, EMF for the moving coil, and A cosine theta, delta B over delta T, and A cosine 0, B2 minus B1 over T. Replace negative and 256, area 0.025, cosine 0, 1, B2, 0, minus 0.25. Negative with negative cancel, divided by 0.75. EMF is equal to, by calculator, 0.21 volt. In this way, you can solve this question. It's a very easy question and very good question. The last question in this section, question 4. Electric guitar strings. The strings of the electrical guitar, we have two types of guitar, electric guitar and normal guitar. In electric guitar, the strings are made of ferromagnetic materials that can be magnetized. What do you mean by ferromagnetic material? It can be magnetized. Okay. The strings lie closely over and perpendicular to the coil of wire. Inside the coil are permanent magnets. Inside the coil that fixes with the string, there will be a permanent magnets that magnetize the segment of the string overhead. Using this arrangement, explain how the vibrations of plucked string produces an electrical signal in the same frequency as a vibration of the string. Electrical guitar can be played by connecting with an AC external source, okay, an AC source that has a frequency, and when the strings are plugged, because the strings made of the ferromagnetic material and can be magnetized, this ferromagnetic material, when it is vibrated inside this coil, there will be a permanent magnetic field. When the strings plugged induces the current. The current will be induced by vibrating the string of the electrical guitar. This vibrating of the string, it goes to induces the current in the strings, okay? and this induced current has the same frequency, and the frequency of the induced current of the string that resulted from the plucking of the string has the same or matches the frequency of the source. When the magnetized strings vibrate, the strength of their magnetic field changes periodically with respect to the wire loops in the coil, inducing an EMF and current in the coil. The vibrations in the induced current match same frequencies and amplitudes of the sounds produced on the vibrating strings. Guys, we finished section 1 and we solved all questions that related with section 1 in chapter 6. We have some extra questions in this section. If you remember, we studied by moving both insulator and conductor into the magnetic field, it experiences a magnetic force. But this magnetic force cannot separate the positive charge and negative charge in an insulator. So that is why no EMF, no current induced in insulator material. But by moving conductor into the magnetic field, EMF and current induced in the conductor. By moving which of the following perpendicular to the uniform magnetic field experiences a magnetic force? Conductor, A conductor, B insulator, C both conductor and insulator, none of them. The correct answer is C, because magnetic force, there will be a magnetic force in both conductor and insulator, but this magnetic force cannot separate positive charge and negative charge in insulator. Another question, by moving which of the following perpendicular to uniform magnetic field, EMF induced? Only by moving conductor, okay? But by moving insulator, EMF is not induced, current is not induced. But by moving insulator, magnetic force experiences a force on the insulator. By moving which of the following perpendicular to uniform magnetic field, current is induced? Closed circuit. Why? Because current is induced only in closed circuit. It's not like EMF and electromotive force. Electromotive force can be induced in both open circuit and closed circuit. So to remind you the equivalence of the units, so it's very important, like the equivalence of Henry, equivalence of Weber, Tesla, Volt. So these equivalents are very important. Pay close attention, please. Let's go to the section 2 in chapter 6. Section 2 in chapter 6 about generator, motor, and mutual inductance. In this section, guys, section 2 in chapter 6, we have 3 topics: generator, motor, and mutual inductance. So first of all, I would like to explain the different types of the current before start explaining section 2. Guys, we have many different types of current. The types of current AC current, DC current. AC current, alternating current, DC current. And DC current can be resolved into can be divided into 2 types. DC, we have 2 different types of DC current. DC pulsating current, DC pulsating current, and DC battery. The DC current of what? Of battery. We have 2 main types of current, AC and DC. And DC can be classified into and can be divided into 2 types: DC pulsating current in generator and DC of battery. In AC current, guys, be careful. So you have to keep in your mind, in AC current, both magnitude and direction of the current changes continuously. In AC current, both magnitude and direction of current changes continuously. How? Look, during the generating AC current, the magnitude of the current here is 0. Also at this point is 0. But here is maximum. What happened to the magnitude of the current during AC current? Its magnitude changes continuously. 0, maximum, 0, maximum, 0, maximum. So how about the direction? The direction also changes continuously. Here we have positive, here we have negative. Positive, negative, positive, negative. In AC current, which of the following changes? Only the magnitude of the current? No. Only the direction of the current? No. Both magnitude and direction changes continuously in AC current? Yes, absolutely. Okay, so this is very important. Be careful. But in DC pulsating current, only the magnitude changes. Look, we don't have negative part here because of the commutator in DC generator. Only the magnitude changes. The direction of the current doesn't change in DC pulsating current. In which of the following current the direction doesn't change? AC, DC pulsating, DC battery, in DC pulsating and DC battery, both. Okay? What is the difference between DC pulsating current and AC current? In DC pulsating current, only magnitude changes. Direction doesn't change. How about the DC of battery? The DC of battery, the situation here is completely different. Why? Because neither magnitude nor direction of the DC battery of the current doesn't change. Magnitude stay constant, direction still stay constant. In DC current, there will be no change in magnitude, there will be no change in direction. Like a battery. The current that produced by a battery is moving in one direction and its magnitude doesn't change. The first definition in this section is generator. What is generator? A machine that converts mechanical energy into electrical energy. In generator, mechanical energy is converted to what? Electrical energy. How? Like by falling water, by a windmill, or burning fuel. It goes to warming the water and becomes vapor, and this vapor, this steam, it heats the blades of the turbine. It goes to rotating the object. So we need a source, an external source to rotating the coil into the magnetic field. This external source may be wind, like a windmill, maybe falling water, like in a dam. In a dam, water is collected and it flows through the pipe, and this potential energy, that storage in the dam, it converted to the kinetic energy. So this flow and this motion of the water in the dam heats the blades of the turbine. It goes to rotating. When the coil is rotating because of the falling water, induces the current. So this is generator. Look at this video. It's about how falling water, it goes to rotating the coil or armature in generator. Guys, look at this video. The falling water this is dam. The falling water is falling because of the gravitational potential energy stored. This gravitational potential energy is converted to kinetic energy. This kinetic energy, it means that this movement of water, falling water hits the blade. This is the blade of the turbine of the generator. Inside this generator, we have armature. This is turbine, generator here, and this rotating armature and coil into the magnetic field produces the electricity. This is the flow free charge. This is the free charge, free negative charge flows through the rotating loop into the magnetic field. This is flow of charge, negative charge. This is electricity. This is current. Induced current by dam, by falling water. And also now I'm going to show you a simulation about the generator. Good simulation. We don't have network, sorry. Okay, let's go back to our pamphlet. Guys, look. A generator, a machine that converts mechanical energy into electrical energy. Another way to induce a current is to change the orientation of the loop, rotating the loop. By changing the orientation of the loop, the theta and the angle of the normal of the loop changes with the respected with the magnetic field. By changing the orientation and the angle between the magnetic field and the normal of the loop, the magnetic flux changes. When magnetic flux changes, current induced and EMF induced in the coil. How? If you remember, we said that flux is equal to what? A, B, cosine theta. How can we change flux? By changing area, by changing magnetic field, or by changing the orientation angle. By changing area, if you remember, EMF is equal to negative NB cosine theta, changing what? Changing area. When the area of the coil changes, you have to use this relation to determine what? EMF. And by changing the magnetic field, you have to use this relation. Change magnetic field over time. Faraday's law for moving coil. For what? This is for moving coil, not rotating. Okay? Changing magnetic field and changing the area of the loop by moving the coil, not by rotating. But EMF for generator is equal to NAB omega sine theta. By changing what? By changing area. By changing what? By changing area, magnetic flux also changes. The orientation of the loop. By changing area, EMF induced when the coil is rotating. When the coil is rotating. For rotating coil we have sine, but for moving coil we have cosine. On what principles does an electric generator operate? Faraday's law of electromagnetic induction. Generator based on what? Faraday's law of electromagnetic induction. Give some examples for the production of electric energy in a power plant and coil rotation. In a hydraulic plant, falling water directed against the blades of a turbine causes the turbine to turn. In a coal or natural gas burning plant, energy produced by burning fuel, by burning what? Fuel, is used to convert water to steam. Convert what? Convert water to steam. And this steam is directed against heat the turbine blades to turn the turbine. Basically, a generator uses the turbine's rotary motion to turn a wire loop in a magnetic field. How an induced EMF produces in generator? When the coil is rotated in a uniform magnetic field. When a coil is rotating, it means that changing the orientation of the plane of the loop in a magnetic field. Guys, we have two types of generator. Two types of generator. AC generator and DC generator. In AC generator, the generator gives us a current that it is magnetic and direction changes continuously. In which type of generator both magnetic and direction of the current changes? In AC generator. AC generator, according to its name, it came from alternating current. A, alternating. C is current. Alternating current, it means that it is current, it is direction, and it is magnetic changes. Okay? So the current will be like a sine wave. Both magnetic and direction changes. Magnetic changes because from 0 reaches to maximum, and from maximum reaches to 0. So can we see magnetic changes? Yes, of course. How about the direction? The direction here is positive, but here is negative. Positive, negative. Both magnetic and direction changes in AC generator. The magnetic and direction of current, this is current, changes continuously. This is current. But in DC generator, DC pulsating generator, only the magnitude changes. Its direction doesn't change. The direction does not change because of commutator. In which type of generator? In which types of generator only the magnitude changes? In DC generator. Okay? In DC generator only the magnitude changes. This is the types of generator. AC generator, a generator that produces alternating current. Both direction and magnitude of the current changes. The main components of AC generator. The components of what? AC generators. Components of AC generator. Components of AC generator. We have four main parts or four main components of AC generator. Now I will explain one by one. Magnetic field. A coil of wire conducting loop. Conducting loop. Armature. A coil. Number 3, 2 slip rings. 2 slip rings. The last component of AC generator, 2 brushes. Okay, now I'm going to draw a figure of AC generator. We have a magnetic field. A permanent magnetic field. Okay, north-south. This is permanent magnetic field. The magnetic field usually comes from north into the south. This is magnetic field, permanent magnetic field. And we have a conducting loop. What? Conducting loop. This is conducting loop. A conducting loop. Magnetic field, a conducting loop into this magnetic field. And this conducting loop must be fixed with the shaft, and this shaft will rotate by any source like falling water, by steam, or by any other sources. Okay, so this coil must be rotate in order to induce current in this coil. And we have 2 slip rings. How many slip rings do we have? 2. Guys, be careful. We have 2 slip rings. The first slip ring and the second slip rings. In AC generator, we have 2 slip rings. We have 2 slip rings, okay? And this 2 slip ring is contacted with the 2 brushes. Also, we have what? 2 brushes. How many brushes do you have? 2. And the 2 brushes connected with what? With the external, with the light bulb, with the slip rings, okay? To connect and maintain connection between external circuit and internal circuit. As the coil rotating into this magnetic field by falling water or by any other sources, when this coil is rotating, the current induced in this coil. The current induced in this coil. When the current induced in this coil, the current passes through this loop, and the flow of charge transfers from the 2 slip rings into the 2 brushes. Okay, without brushes, without 2 slip rings and the 2 brushes, if we connected the 2 wires with this armature, with this conducting loop, the wires will twist together, entangle it together. Okay, to avoid entangling and twisting the wires, these 2 wires, we have to put the 2 slip rings and the 2 brushes. Okay, because of these 2 slip rings and these 2 brushes, the wires does not and the loop does not twist and entangle to each other. So these are the components of the AC generator. We have magnetic field, conducting loop, 2 slip rings, and 2 brushes. This is the 2 brushes. Okay. Now I'm going to show you a piece of video about the AC generator, a very useful video for the students. I'm sure that you will get benefit from this video, so because it's very helpful to understanding about how AC generator works and the components of AC generator. Guys, look at this video.
What you're looking at is a very simple alternating current or AC generator.
AC generator. We have a galvanometer to indicate the induced current that induces in this loop by rotating the coil. We have a magnetic field. This is permanent magnetic field. North, south. We have a conducting loop, armature, and two slip rings and two brushes. This needle of the galvanometer indicates the presence and zeros of the induced current. If the needle is located at 0, it means that there is no current in the wire, in the loop, no current induced. But when the needle deflected to the maximum displacement, it means that the current is induced in the loop as a result of rotating armature in this magnetic field.
Mechanical energy into electrical energy. This part is called the armature.
Armature or loop. This is loop.
Electricity generated by its rotation between two magnets.
By rotating between two magnetic fields.
Works, one half has been called the element. The armature can be rotated in various ways, for example using pressurized steam, as in a power plant, a flow of water from a dam, or a flow of air from a wind turbine. These parts are called slip rings. They are also made of metal and are connected to the armature. The slip rings and the armature.
The two slip ring is rotating. But the brushes on the wire doesn't rotate. Why? Because if the wire is rotating, they will entangle and twist together.
So they provide an electron flow within the system. In order to determine the magnitude and direction of current, a galvanometer is attached. When the armature starts to rotate, an electric current is formed. This is because the magnetic flux changes over time. Magnetic flux is a measurement of the total magnetic field that passes through the surface. In a field that rotate, an electric current is formed. This is because the magnet.
Guys, look. Now, the plane of the loop is perpendicular to the magnetic field. In generator, when plane of the loop is perpendicular, rotating coil, like generator, and moving coil. We studied the moving coil in section 1. In both cases, when plane of the loop is perpendicular, if plane of the loop of coil, if plane of coil or loop is perpendicular to the magnetic field, theta is equal to what? Theta is equal to 0. When theta is equal to 0 in rotating coil, EMF is equal to 0. Induced current is equal to 0 in generator. In what? In generator. In generator, when plane of the loop is perpendicular, no current induced, no EMF induced in this conducting loop. And this situation is completely different with the moving coil that we studied in section 1. In section 1, by moving coil, not rotating, guys, be careful. By moving coil into the magnetic field, if the plane of the loop is perpendicular, EMF and current becomes maximum value. In moving coil, if plane of the loop is perpendicular to the magnetic field, theta still 0. In both cases, guys, when we say plane of the loop is perpendicular, it means area vector is parallel to the magnetic field. So we have to count the angle between area vector and magnetic field, not plane of the loop. But when we say plane of the loop perpendicular, area vector parallel, angle 0. And in the case when plane of the loop is parallel, area vector is perpendicular magnetic field. Area vector will be perpendicular to to the magnetic field, an angle becomes 90. Okay? When plane of the loop is perpendicular to the magnetic field, angle between A and B becomes 0. And EMF has maximum value, current also has maximum value. But in moving coil, in what? Moving coil. Why? Because in generator, the equation of induced EMF, in generator, EMF is equal to what? N A B omega sine theta. But for moving coil, EMF is equal to what? Is equal to negative by changing like magnetic field, or by changing delta AB cosine theta over time. Guys, look, why when plane of the loop is perpendicular, angle 0, EMF is maximum in moving coil? Because cosine 0 is equal to maximum, equal to 1. But in rotating coil, in generator, the situation is completely different. Why when the plane of the loop is perpendicular? Same as in moving coil, theta 0, EMF 0, current is 0, because we have sine. Sine 0 equal to 0. But sine 90, sorry, cosine 0, but cosine 0 is equal to maximum. That's all. Okay? Now plane of the loop is perpendicular. Plane of the loop is perpendicular. Guys, look. Plane of the loop is perpendicular. Look. When plane of the loop is perpendicular, the area vector is parallel. Area vector is parallel to the magnetic field. Same direction. Field from north to south. Angle between A and B, when plane of the loop is perpendicular, angle between them is equal to what? Equal to 0. When angle equal to 0, sine 0, 0. EMF 0. Current 0. The needle of the deflector is the deflection of the needle is located at 0. Okay?
Magnetic flux changes over time. Magnetic flux is a measurement of the total magnetic field that passes through the surface.
Guys, look. In this case, plane of the loop is parallel. When plane of the loop is parallel, area vector with magnetic field, angle between area vector, this is area vector. This is area vector, guys. This is area vector, okay? And the angle, this is magnetic field. Angle between them is what? Perpendicular. Sine 90 is equal to maximum. Okay, change in magnetic flux here is maximum. When plane of the loop is parallel, EMF is maximum. Okay?
Notice that is 0.
But if plane of the loop is perpendicular, as you can see in this video, when plane is perpendicular, area vector with magnetic field, area vector with a magnetic field, they have the same. Area vector and magnetic field, they have the same angle. Angle 0, sine 0, 0, EMF 0, if the plane is perpendicular in generator. Okay? Let's continue watching the video.
Flow and an electric current.
As the plane makes parallel to the magnetic field, EMF becomes maximum, reaches maximum.
And so the current reaches a maximum too.
In this case, now plane of the loop is parallel. When plane of the loop is parallel to the magnetic field, what happens to the area vector? Area vector is perpendicular. Area vector is what? Perpendicular. Look. Area vector perpendicular to what? To the magnetic field. Angle is equal to what? When plane is parallel, angle 90. When angle is 90, EMF maximum. Current absolutely maximum. Okay?
The armature continues to rotate. The change of the magnetic flux gradually decreases, and consequently, the current decreases as well. When the yellow
as the current makes perpendicular to the magnetic plane of the loop perpendicular, current reaches zero again.
And because the change of magnetic flux is zero at this point, the current is zero as well. Up to this stage, according to Fleming's right-hand rule, the current's direction is inward. Current drops to zero. The cycle is completed. Between half and complete cycle, Fleming's right-hand rule indicates that the direction of current is outward.
After each half cycle, the direction of the current changes. Maximum.
Every half
zero.
In an AC generator, the three-quarter cycle, the electric current reaches a maximum.
As the plane becomes perpendicular, becomes zero and continues.
After every half cycle, the direction of the current
changes continuously. So that is why in AC generator, both magnetic and direction changes continuously. I hope you benefited from this video about the AC generator. Okay, let's go back to our pamphlet. Okay. And we studied the components of the AC generator. AC generator produces an alternating current that it is magnetic and direction changes continuously. Guys, look at this figure. This question has been brought in 2021, 2022. In AC generator, we have 4 marks, A, B, C, D. At mark A and C, we know that the amount of current is 0. At A and C, the amount of EMF 0, current 0, and the orientation of the coil here is perpendicular to the magnetic field. At point A and point C, the plane of the loop is perpendicular because EMF is 0. But point B and point D, plane of the loop is parallel. Why? Because at point B and D, induced EMF and induced current is maximum. That is why the plane of the loop must be parallel. Question 13, review assess. List the essential components of an electric generator and explain the role of each component in generating an alternating EMF. As we know, there are 4 components of AC generator: magnetic field, induces EMF, turning coil, wire coil, a coil of wire, conductors induced current, slip rings, maintain contact with the rest of circuit by means of conductivity brush or brushes. The 2 graphite brushes, connection to the external circuit and internal circuit. So that's all about the AC generator. Inshallah, in the next lesson, we will continue to explain the other topics in this section about the DC generator and how can you determine DC EMF in generator, and also we will study the motors and mutual inductance. Thank you for listening. Hope you get benefited from my lesson.